In this lesson, you will learn what a magnet is and how it physically interacts with other magnets. You have probably already seen and used magnets. They appear in many forms. You probably played with magnets as a child, and there are magnets which are used around the house, such as the magnets which are used to stick notes to the fridge door. Legend has it that magnets were discovered by a Greek shepherd who walked across a field containing dark red stones, which pulled the nails out of his sandals. These stones were given the name magnetite or lodestone. Magnetite or lodestone is the most magnetic of all the naturally occurring minerals on Earth. A magnet is an object that has a magnetic field. You may think that this doesn't sound like a very helpful definition of a magnet, but this definition does emphasize the fact that when we call something a magnet, we are not describing what the object is made from, as we do when we say that something is made from metal or plastic, etc. Our definition is really saying that an object is a magnet when it behaves like a magnet. For instance, here is something picking up some common metal objects. It would be reasonable to call this something a bar magnet. If, however, it stops acting like a magnet, we may no longer call it a magnet. So what then are the qualities by which we recognize a magnet? How does a magnet behave? The first thing that we notice about a magnet is that it attracts towards itself ferrous materials, such as iron, nickel, and cobalt, but it does not attract other materials, such as plastic, glass, or even some other metals, like aluminium. The materials that can be attracted by a magnet are termed magnetic materials, or more precisely, ferromagnetic materials. Therefore, magnetism is simply the name we give to that property of an object or body which causes it to act like a magnet. The next thing we need to look at is how a magnet reacts in the presence of other magnets. Two magnets, when placed near each other, either repel or attract each other. This unusual behavior is one of the trademarks of magnets. We can explain this behavior by referring to the concept of magnetic polarity. When we talk about magnetic polarity, we are talking about the north and south poles of a magnet. All magnets possess a north pole and a south pole. You will never find a magnet that has a single pole. When the ends of two magnets are brought together, they either repel or attract each other. If the magnetic poles that are brought together are the same sort of pole, two north poles for instance, then the magnets repel each other. The same thing happens if two south poles are brought together. If one of the magnets is rotated so that its other pole is brought close to the second magnet, then the two magnets will attract each other. So we can say that unlike magnetic poles attract each other. The magnetic effects of a magnet are produced by an invisible force that surrounds the magnet. This force is known as a magnetic field. To discover the layout of a magnet's field, we can suspend a magnet so that it is free to rotate as shown. The magnet under the pencil is free to rotate both clockwise and anti-clockwise. However, in the presence of a second magnet, it does not move about randomly, and it does not stop in just any orientation. The suspended magnet will come to rest, pointing in a very specific direction. which depends on its position relative to the other magnet. Let's now view the magnets from above. We will observe and take note of the various directions in which the suspended magnet comes to rest when it is placed in different positions relative to the fixed magnet, to see if there is a pattern to it. If we mark the different directions in which the suspended magnet comes to rest, with arrows pointing from the magnet's south pole to its north pole, it is easier to see the pattern that is emerging. After some time, this picture emerges. The lines that we have plotted are called lines of flux, or lines of force. The lines of flux show the direction in which a freely suspended magnet will come to rest. This direction is referred to as the direction of the field. Notice how the lines of flux are tightly packed together at the poles of the fixed magnet and are much more spread out elsewhere. The regions where the lines of flux are closest together are the regions where the effect of the magnet is strongest. Although in our diagram some of the lines are shown incomplete, they are always a continuous loop from one pole to the other. We have seen that a freely suspended magnet comes to rest along the field lines of a fixed magnet. But in what direction will it come to rest if there is no other magnet nearby? A freely suspended magnet, even when it appears that there are no other magnets nearby, does not come to rest in a random direction. No matter what direction the magnet is pointing in when it is released and begins its swing, it always ends up pointing in the same direction. This is because the suspended magnet is still being affected by a magnetic field. The magnetic field we refer to is one that everyone on our planet experiences every day. It is the magnetic field created by the Earth itself. The Earth has a magnetic field of its own, which acts as if it is created by a huge bar magnet at the Earth's core. A freely suspended magnet will come to rest aligned with the Earth's magnetic field. The atoms and molecules of magnetic materials behave like micromagnets themselves. It is the total magnetic field from all of these microscopic magnets which gives us the magnetic field we detect around the magnet itself. For simplicity, we will use arrows with points on their north poles to simulate the micromagnets. If the micromagnets are all pointing in the same direction, then their individual fields all reinforce one another. The diagram here shows all the micromagnets pointing in the same direction. A standard bar magnet is just a magnetic material, such as iron or steel, in which some of its micromagnets are pointing in the same direction. If the micromagnets are all pointing in random directions, their fields cancel one another out. So an iron bar, which does not behave like a magnet, is depicted like this, with its internal micromagnets all pointing in random directions. A ferromagnetic material is a material in which the internal micromagnets can be rotated and fixed in alignment with one another. This can be done by stroking it in one direction with the pole of a magnet. Here, the north pole of the magnet is pulled along an iron bar, pulling all of the south poles of the bar's micromagnets into one direction, thereby creating more and more micromagnets which are pointing in the same direction. Notice how the originally disordered micromagnets become aligned as they are pulled into place by the magnet. A magnet where all the internal micromagnets are pointing in the same direction is said to be saturated. It cannot be magnetized anymore. The ease with which the micromagnets are realigned depends on the material in which they exist. The term magnetically soft describes a material in which the micromagnets can be realigned easily. Iron is a typical example of a magnetically soft metal. It can be easily magnetized, but it rapidly loses its magnetic properties. Magnetically soft iron is said to have a low magnetic retentivity. You will not be surprised to learn that a magnetically hard material contains micromagnets which are far more difficult to realign than those of a magnetically soft material. A common hard magnetic material is steel. A hard material is one that requires a lot of effort to magnetize. However, once it is magnetized, a hard material contains its magnetism much longer than a magnetically soft material will. So permanent magnets are made from hard magnetic material. The reason why magnetic materials are attracted to magnets is because the magnet's field aligns sufficient of the magnetic material's micromagnets to turn it temporarily into a magnet with opposite poles. You have learned that the internal micromagnets in a ferromagnetic material can be aligned, causing the object to become a magnet. However, this process can be reversed. The alignment of the micromagnets of a magnet can be broken, so that the object is no longer a magnet. The breaking of the alignment of micromagnets can be achieved in a number of ways. High temperatures can disrupt the orderly alignment of the micromagnets in a magnet, causing it to stop being a magnet. Another way of disrupting the micromagnets of a magnet is simply to drop it onto a hard floor, or to physically strike or knock it. This has the effect of shaking up the micromagnets, randomizing them, and destroying whatever alignment they had within the magnet. A third way is to place the material inside a solenoid, which is supplied with an alternating current. Solenoids are fully explained in another lesson. In the final part of this lesson, we will examine the nature and orientation of the lines of flux when permanent bar magnets are brought together in different configurations, and when a bar magnet is placed near iron objects. Here is the first situation that we are going to consider. On the left is a bar magnet with its north pole pointing to the right, and on the right there is a soft iron bar. If we trace out the lines of flux, we will see that not only are there lines coming from the magnet, but there are also lines coming from the iron bar. This shows that the permanent magnet has induced the micromagnets in the iron bar to align, so that the iron bar is now acting like a magnet. This increases the flux density from what are now two magnets. This property of a magnetic material to increase a magnet's flux density is known as permeability. When the soft iron bar is removed from the magnetic field, it loses most of its magnetism. The little magnetism which remains in the iron bar is known as residual magnetism. Here, two magnets are placed in line, with the north pole of one magnet facing the south pole of the other. The magnets attract each other. If they were not securely fixed in place, they would actually come together. The lines of flux between the two magnets are very tightly packed together. This is because the lines of flux from the two magnets are reinforcing one another to create a dense area of magnetic flux. Here, one of the magnets has been flipped around, swapping over north and south poles. The magnetic lines of flux between the magnets now appears to be deflected. This is caused by the fact that lines of flux can never cross each other. The lines of flux from the north pole of each magnet are pushing the two magnets apart. There is an indication that the two magnets are repelling each other. That is the end of the lesson. Here is a summary of the important points which have been made in this lesson. A magnet is an object which has a magnetic field, and which behaves like a magnet. This magnetic field is characterized by lines of magnetic flux, which trace a path from the north pole of the magnet to the south pole. Like magnetic poles repel each other. Unlike magnetic poles attract each other. For example, the north pole on one magnet will attract the south poles of any other magnets that are brought close to it. Ferromagnetic materials, if they are not magnets themselves, are attracted towards both the north pole and the south pole of a magnet. If a ferromagnetic material has some of its internal micromagnets pointing in the same direction, then that material is itself a magnet. A magnetically soft material has micromagnets that are easy to realign. Less effort is required to magnetize or demagnetize a magnetically soft material than a magnetically hard material. An external magnetic field can induce a ferromagnetic object to become a magnet. Heating a magnet, or physically shocking it, or placing it inside a solenoid which is supplied with an alternating current, can cause the internal micromagnets in that magnet to become unaligned, stopping the material acting as a magnet.